Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 29, and it is entitled Wave Characteristics of Light. We're going to see in future lessons that light can also be considered to behave as a particle, but today what we want to do is to focus on wave characteristics of light. We say that light is a wave. Actually, what it is a piece of electricity and a piece of magnetism. It's called an electromagnetic wave, and we will see that the electric field and the magnetic field that makes up this wave will be in directions that are perpendicular to each other. So all the wave characteristics that we've seen that can apply to sound or to waves in strings or to waves on water, we can carry all of that machinery over to talk about light. One important thing about light that is different than other types of waves is that light is able to travel through a vacuum, whereas mechanical waves cannot travel through a vacuum. Now, light can also travel through materials, like it can travel through a piece of glass, or it can travel through other objects, and we'll see that certain materials will be transparent to certain frequencies of light, certain wavelengths, and will be opaque to other frequencies and wavelengths. So it's possible for light to travel through a medium, but it's also possible for it to travel in a vacuum. It travels through the vacuum of space. That's how the sunlight gets to us. One thing you'll need to know about light is the fact that the electromagnetic spectrum, the light spectrum, is broken up into several sections. You've learned these before. Low frequency, long wavelength part is called radio waves, and then working our way up in frequency or down in wavelength, you get microwaves, infrared, visible, ultraviolet, X-ray, and gamma radiation. And you need to know those sections of the electromagnetic spectrum. Since we bring up wavelength and frequency, you'll remember the relationship between them has to do with the speed of the wave. The speed of the wave is equal to the wavelength times the frequency. This equation applies to light as well. If light is traveling in a vacuum, then the speed of light has a special symbol and a number that you should know. That symbol is c, that stands for celeritas, or swiftness. Celeritas is Latin root word for acceleration, celeritas, acceleration. The idea is that it moves really fast, and its speed is 3 times 10 to the 8th meters per second. The kind of electromagnetic radiation that our eyes are sensitive to is the visible part of the spectrum, and it's important that you know what the colors are, what their ranking is, and what the wavelengths correspond to for the extreme parts of the visible spectrum. So you ought to know Roy G. Biv, and you need to know that the red wavelengths are on the order of about 700 nanometers. Violet wavelengths are on the order of about 400 nanometers. Back in lesson 23, we talked about reflection, which is the bouncing of a wave off of a boundary. Now we want to discuss something that's called refraction. Refraction refers to the bending of a wave as it crosses a boundary between two different materials, and the bending occurs as a result of the change of the speed of the wave as it passes from one material to another. If we think back to our diagram involving rays that are reflected from a surface, let's sketch a diagram that shows a reflected wave and a refracted wave. So imagine I take a laser, a small pencil of light, and I shine it at a glass surface. So you can imagine I have a transparent piece of glass, and I'm just showing the top surface of the glass, and I send an incident beam of light in, maybe from a laser pointer. Part of that ray is going to bounce, it's going to reflect, and part of that ray is going to be transmitted, and that transmitted ray, we would say, gets refracted. Let's show the reflected ray first. Remember, what we do is we first sketch a normal to the boundary at the point where the incident ray hits the boundary. There are a couple of angles involved, and the one that we're interested in is going to be measured with respect to the normal to the boundary where the incident ray hits. And we'll call that angle between the normal and the incident ray the angle of incidence, theta I. In this particular diagram, I've drawn theta I equal to about 50 degrees. Now there's going to be a reflected ray, and the law of reflection tells us that the reflected angle is also going to be 50 degrees in this case. Whatever the incident angle is, that's what the reflected angle is going to be. But now I'm going to have a piece of that ray that's going to pass into the glass. It turns out that the light doesn't travel as fast in the glass as it does in the air. The glass is more dense, and as a result there is a slowing down of the wave as it passes into the glass. Now, if there were no glass there, the incident ray would just pass along the line that it's traveling on already. But now there is a piece of glass there. The incident ray bends, and it turns out that it is going to bend away from the path that it would follow if there were no glass present. It bends toward the normal because it slows down. So we call that a refracted ray or a transmitted ray. And since we used a subscript r to represent reflected ray, then for this angle, the angle between the normal to the boundary and the refracted or transmitted ray, I'll call that theta t. If the ray were to travel across a boundary and end up in a medium that is less dense than its incident medium, then we would say the refracted ray bends away from the normal. In this case, the ray slows down, and so it bends towards the normal. And we may talk about why that is when we get to class sometime. The more optically dense the medium is, the slower the light wave is going to travel when it gets into it. This refraction is not just true for light waves, it happens for any kind of waves. Water waves, sound waves, anything. The idea is that if the wave slows down and crosses the boundary, then the refraction occurs toward the normal to the boundary. On the other hand, if the wave speeds up when it crosses the boundary, it bends away from the normal. There's an example in your textbook showing this, and that example is example 29.2. A ray of light is incident on a triangular shaped piece of glass as shown. Sketch the ray of light as it passes through the triangle and exits back through the air. Now I have enlarged this diagram very large because I want to show some details. We have two boundaries that are present here. The first boundary is the straight vertical boundary that we see where the light comes in. The light's going to be traveling from air into glass when it crosses this boundary, so it's going from a less optically dense medium to a more optically dense medium. Now, when that light gets into the glass, it's going to travel through the glass until it gets to the slanted edge, and then it's going to pass from a more optically dense to a less optically dense. It's going to pass back into the air. Let's see how we would construct this. First of all, let's take a look at boundary number 1, which is right there. So there is my incident ray, and I need to sketch a normal to the boundary at that point. We would say this ray strikes the boundary at normal incidence. Well, what does the normal look like? It's actually going to be along the same line that the incident ray travels. It looks like this. On the left side of the boundary, I've sketched the normal line in white, and on the right side of the boundary, I've sketched it in black. Well, now, if the ray hits at normal incidence, it's not going to bend because it's just going to pass straight through. What ends up happening is the ray slows down. So the transmitted ray is going to lie along that line of normal incidence, but it will have changed its speed when it crosses into the glass. I'm going to show the transmitted ray in orange. Now let me reiterate. The incident ray is coming from air. It's traveling fast. When it crosses into the glass, it actually slows down. It doesn't bend at this point because I hit it normal incidence, but it does slow down. Okay, so now the light is inside the glass. It gets to the next boundary. What happens? Well, it hits this boundary at an angle, and since it's going to pass from a more dense to a less dense material, it's going to bend away from the normal. So let me sketch a normal line at the place where the ray strikes the boundary. Remember, the normal line is a line that is perpendicular to the boundary at the point where the ray strikes it. So now we're looking at boundary number 2, and we can see that there is some angle of incidence that this incident ray, this orange ray, makes with the boundary. Now the light passes from a more dense optically dense piece of material to a less optically dense piece of material. It's going to bend away from that normal line. If there were no boundary there at all, the ray would continue to travel straight on. But now the transmitted ray bends, and it bends away from the normal, away from that direction that the ray would travel if there were no boundary in place. So there's how you would approach this particular problem. Reviewing, coming from air into glass at normal incidence, there's no bending that occurs. The wave changes its speed. It slows down as it enters the glass. Then when it gets to the second boundary, it changes speed again. But now it strikes this boundary at some angle as a result of the geometry of the glass, and the transmitted wave across that boundary gets bent away from the normal.